Regardless of the controlling property, the material used in a part designed for fatigue resistance must possess an acceptable combination of many properties, and data may not be available for all specific materials, conditions, and forms. Summary: fatigue fracture. Stage 1, initiation. Stage 2, propagation. Stage 3, fracture. Fatigue fracture characteristics: striations, beach marks, final rupture, ductile or brittle. Variables affecting fatigue failure: overstress, stress concentrations, frequency of loading, type of loading, residual stress. Practices affecting fatigue life. With so much diversity in function, loads, stresses, materials, and environments, simple rules for fatigue-resistant design cannot be stated. However, a number of useful practices can be defined. When applied with good engineering judgment, these practices can reduce significantly the probability of fatigue failure. The available data are normally shown for a specific type of loading, specimen size, and surface roughness. Design guides that can minimize interference at the line of contact between mating parts are to provide generous fillets and radii, and to design parts with minimum mismatch at installation. This provides the lowest residual and preload tensile strains. The fatigue strength of good as-welded joints depends on the stress state in the load path weldment, the stress concentration toe of the weld, the condition of material in the heat-affected zone, and the presence or absence of inclusions and other imperfections in the weld. The fatigue strength of as-welded joints can be increased by cold working. The growth of cracks can be inhibited by introducing compressive residual stresses and redistributing fabrication stresses. Poor welding practices can create surface discontinuities, giving rise to stress razors where bending fatigue and torsional fatigue cracks can originate. Craters, undercutting, underbead cracks, and arc strikes are typical surface discontinuities from welding. Subsurface discontinuities, such as flux inclusions, incomplete fusion, and inadequate joint penetration, can originate cracking in parts loaded in tension, bending, and torsion. Under low cycle fatigue, the fatigue life of many metals is independent of grain size. In contrast, under high cycle fatigue, the fatigue life of many metals is increased when grain size is reduced. However, the effect of grain size on high cycle fatigue properties is difficult to assess, since many microstructures are altered by the same treatments that alter grain size. An improvement in resistance to high cycle fatigue brought about in some alloys by a decrease in grain size may be offset by a harmful effect on another property. For example, a decrease in grain size raises the smooth bar fatigue limit in some steels, but the small grain size may increase the notch sensitivity in these steels. The net result may be no improvement and no resistance to notch bar sensitivity. Discontinuities within a metal, either at the surface or subsurface, can adversely affect fatigue strength. These discontinuities may arise from primary or secondary working of the material or from melting practices. They may also be a characteristic of a particular alloy system. All wrought metal is shaped by thermal-mechanical processing, generally by rolling, forging, pressing, or drawing. The movement of metal during these processes makes them susceptible to the formation of surface discontinuities. Laps, seams, and cold shuts can form. Oxides, slivers of the base material, or foreign material can be embedded into the surface. These surface imperfections produce notches of unknown severity that act as stress razors under load. They may also serve as sites for crack initiation during fabrication or in service. Burning results from heating a metal to a temperature so close to its melting point that permanent, irreversible damage is caused to the metal, by intergranular oxidation or incipient melting. Burned steel usually contains both oxide films and voids or cracks at the boundaries of very large grains. These act as nuclei for fatigue cracking. Gross non-metallic inclusions at or near the surface are detrimental. They act as stress raisers, forming points for the initiation of fatigue cracks. The larger the number of discontinuities, the greater the possibility of fatigue failure. Manufacturing operations that greatly affect fatigue strength include machining, grinding, heat treating, straightening, plating, welding, and identification marking. Components intended to withstand severe fatigue conditions should be finished with a fine cut or preferably ground. If possible, the direction of the final cut or grind should be near parallel to the direction of the principal tensile load. Quench cracks frequently cause failure in hardened steel parts. Quench cracks in steel originate from volume changes that occur in hardening. The transformation of austenite to martensite always expands with unfavorable conditions, and this may result in cracking. Many conditions promote the formation of quench cracks. Quenching media that are too severe, sharp edges and rough finishes, hardening temperatures that are too high, and hardening transformation that occurs last in the center of the part. Unless special precautions are taken when heating to high temperatures in an oxidizing atmosphere, the risk of losing carbon from the surface of steel is always present. Steels with severely decarburized surfaces show a marked reduction in fatigue strength. Sometimes components are unintentionally deformed. This can happen during manufacture, in shipping, or in service. Even though deformed plastically, these components can be straightened by any one of several cold or hot methods. But these initial deformations and subsequent working operations can introduce detrimental residual stresses, stress raisers, or cracks. Nicks, scratches, or locally work-hardened surfaces are all potential stress raisers. Plating is usually detrimental to the fatigue strength of plated parts. Carbon and low alloy steels, particularly steels of high hardness, are susceptible to hydrogen damage. The hydrogen is absorbed during the plating cycle and the associated acid cleaning cycles. Hard plating materials, such as chromium, are usually in a state of residual tensile stress after being deposited on the base metal. Cracks develop in the plating material. The cracks act as stress raisers, and if the cyclic stress amplitude is sufficient, the stress raisers may produce cracking in the base metal. Identification marking on components can introduce excessive stresses. The location and method of marking this information is particularly important. Marks should not be in areas of high tensile, bending, or torsional stresses. For castings and forgings, raised letters introduced in the dies or molds are preferred to indented stamps. For marks on machined surfaces, a marking ink is preferable to using an electric etching pencil or vibrating mechanical engraver. A cold steel stamp is probably the most abusive to the steel. However, using steel stamps in a non-stressed area may be preferable to some other type of identification mark in more highly stressed regions. Characters with straight lines tend to cause the most cracks, although characters with rounded corners also cause cracking. If steel stamps must be used, they should be low-stress stamps or dull stamps that will cause the least trouble, particularly if light impressions are made. The stamping should also be located in areas known to be low stress. Thermal fatigue is a residual stress effect. It is caused by simultaneous mechanical restraint and repetitive thermal changes. The thermal expansion is caused by a local temperature increase. The expansion acts against a restraint, usually the harder, stronger, cooler metal adjacent to the heated metal. When hot, compressive yielding may result, and during cooling, the compressive yielding, in turn, causes tensile residual stresses from the thermal contraction. Repetitive thermal cycling can result in fatigue crack formation and propagation each time the metal cools to the lower temperature. The restraint to the thermal expansion may be external, mounts for pipes, exhaust manifolds, or other rigid structures. Or it may be internal, as the cold, strong metal on the inside of a part still unheated by the heat on the outside. Brake shoes heated by friction, clutch plates, and many engine parts are subject to uneven heating. Low cycle thermal fatigue failures can be identified by multiple initiation sites that join randomly by edge sliding to form the main crack, transverse fractures, an oxide wedge filling the crack, and transgranular fracture. True thermal fatigue occurs in such components as internal combustion engines, where thick section cast materials are used. Thermal fatigue also occurs in appliances and heat exchangers, where thin wrought material is used. When cast materials are used, the desirable design features are uniform sections, mild strain gradients, and short flake graphite microstructure. In oil-fired and gas-fired furnace heat exchangers, the thermal cycle is very important. The thermal cycle controls temperature gradients. In thin sections, external constraints are of minor importance. Under certain circumstances, thermal fatigue and stress rupture failures blend into each other. Thermal fatigue is the basic mechanism in failures caused by numerous short heating and cooling cycles. Stress rupture becomes important as the cycle times increase. Stress rupture, therefore, is primarily a long-term rate process. Most thermal fatigue fractures are low cycle, high strain. The fracture surfaces are rough and faceted at or near the initiation sites. They are more fibrous, with shear lips at 45-degree angles in the final fracture area. Thermal fatigue frequently can be prevented by reducing steep thermal gradients. This is brought about by better cooling, less aggressive friction materials, and the use of materials with higher thermal conductivity. The other factor, restraint, can frequently be minimized by designing flexibility into the system. The use of expansion joints and loops, curved sections, bellows, and sliding joints permit the hot sections to float or expand and contract unrestrained. Thus, compressive yielding cannot occur when the metal is hot. In most instances, corrosive environments reduce the fatigue strength or fatigue life of a given material. The effect varies widely, depending primarily on the characteristics of the material-environment combination. The environment affects crack growth rate, the probability of fatigue crack initiation, or both. For many materials, the stress range required to cause fatigue failure in an aggressive environment diminishes progressively with time and with number of cycles compared to an inert environment. This is seen as a progressively wider separation between fatigue curves for inert and aggressive environments. Corrosion fatigue tests on smooth specimens of high-strength steel indicate that very large reductions in fatigue strength or fatigue life can occur in salt water. For instance, the fatigue strength at 10 million cycles could be reduced to as little as 10% of the fatigue strength in dry air. In these tests, the main role of the environment was corrosive attack of the polished surface, creating local stress razors that initiated fatigue cracks. Salt water also increases the crack growth rate in steels, provided the cyclic rate is 6 cycles per second or slower. Surface features of corrosion fatigue crack origins vary with the alloy and with the specific environmental conditions. In carbon steels, for instance, cracks often originate at hemispherical corrosion pits. Often these contain significant amounts of corrosion products. The cracks are predominantly transgranular and may exhibit a slight amount of branching. Except where they intersect the free surface, they resemble fatigue cracks that are not environmentally induced. Surface pitting is not a prerequisite for corrosion fatigue cracking of carbon steels. Corrosion fatigue cracks sometimes occur in the absence of pits. Extensive corrosion often damages fracture surfaces and can make positive identification of the fracture mechanism difficult. The environment may also alter the mode of crack propagation. In hydrogen, for example, fatigue crack growth by quasi-cleavage has been observed. This is considerably different from the typical mode of fatigue crack propagation. Summary: practices affecting fatigue.